Okay. And I'll pause the recording. Okay, so you saw this this cartoon, and we just tried to ask you what was wrong about that. So, any volunteers to tell me what you saw wrong about it? What is strange about that? You can type it in the chat box. Causality is violated. Okay. Anything else? What about information? So it's causality, yes, but also whatever was written there, where did it come from, right? So we will come back to that a bit later today. So for now, I just wanted you to think about it for a bit. Now, let me then get back to the material that we have. And for that, we will use this one. Mm-hmm. Okay, there you go. Can everybody see this? Okay, perfect. So then let's get started. Okay, and there we go. So what we have been doing so far is basically, well, let me just remind you where we were. Let me just take a picture from here so I can see this better. Okay, so we have been doing several things. We started taking a look at the history, and very briefly, what we have been doing is that we talked about the electron, radioactivity, the nucleus, then the neutron was discovered, fission was discovered. We went about what happened there. We went from the original idea of eternal atoms, from this idea of the Greeks that just by thinking they realized that there should be, or there could be, some really essential, really basic building blocks of reality. But we went from that very ambiguous and incomplete idea to realizing that radioactivity is a sign and measure of the instability of atoms. Then we also talked a little bit about nuclear physics, and well, basically particle physics went from impossible to power plants and power sources for spacecraft. And in parallel, we also mentioned this, well, basically what happened in physics was that we went from a description of matter in terms of continuous media to atoms and quantum mechanics. Also, something else that happened was that we went from a few subatomic particles to many. Originally, we talked about the photon, or historically, we knew first about the photon, then the electron, proton, neutron, and neutrino. Then some other, and we already talked about this, that we went to the pion, the muon, then two different neutrinos, and then an explosion of other particles, long-lived particles, other mesons, etc. And also not only mesons, but baryons, meaning, does anybody remember how do we know that a particle is a baryon? Anyone in the chat box? Decaying to neutron or proton, yes. So if when it decays, eventually it produces a neutron or a proton, then we consider it a baryon. And it turned out, because it turns out that there are some particles that always end up being a proton or a neutron, so there was some sort of conservation law. But that happens for baryons and not for mesons. And eventually it was found that there are over 100 hadrons, so things became a little bit messy again. Now, so we have been talking about particle properties, and we discussed all the patterns and relations and symmetries Also, we discussed the fact that we have antiparticles and this eightfold way to describe them, and then that there are 3 generations, etc. Now, another thing of this is that we need to think about reactions and processes. So besides the particles themselves and their properties, we also need to understand how they can combine. And in that combination, in those potential relations between particles, we have conservation laws, and of course, we know several of them, that charge, momentum, and energy, and angular momentum should be conserved. Also, we discovered that baryon number is conserved, and there are 3 different lepton numbers that are conserved. And there are also some that conserve strangeness, other processes don't. So there are several things there that we need to clarify or to understand. Now, all known particles are well described as combinations or members of this little table that we have seen already. So basically, that's the main, well, the elementary particles. And here you see a very partial, very small fraction of the total number of particles that are known, but where you can see several of these combinations. For example, you already know, I imagine, that the proton is a combination of 2 up quarks and a down quark. And if you put together their charges and all the numbers that correspond to them, it works out. Then the neutron is 2 down quarks and an up quark. And there are some other cases, for example, the pion, the neutral pion, because we have also a charged pion, which is either UU bar or DD bar. We're going to think about it today, at least, as UU bar, okay? And that's going to come handy a bit later today. Then in this section, in the new chapter that we're going to hopefully finish this week, we're going to be concentrating on the basic processes that are allowed by the standard model. So now that the last chapter was about history, so that you understood a little bit of where all these particles come from and how they behave a little bit. And now we're going to take a closer look at how they combine. What are as I said last time, on the one hand, we have the players or the pieces of the chess, of this chess game, that we can think of the universe as being a big chess game. So first we have the pieces, and today we're going to take a look at the rules, or what we understand about the rules so far. So then there's a couple of things that it's useful to start thinking about the following. So basically, how we went from quantization to the diagrams that we're going to talk about today. So basically, when and you have already, or most of you have already taken quantum mechanics, and you are probably aware of this, but we're going to try to push it a little bit further than what you've seen. So basically, in a one particle system, you already know that basically when originally classical mechanics described that, what we want is to describe things in terms of position and momentum. And when we went to quantum mechanics, basically what we do is we convert, we replace those two by operators, and those operators help us describe what happens with bound states. When we have a potential well like this one, you know that by taking a closer look at what the Schrödinger equation, or basically the Schrödinger equation allows the wave function to be in that potential, it turns out that the potential states or the possible states of the wave function are discretized, and then we talk about quanta, and those are the different that corresponds to the possible energy levels of that kind of system. And then there's one additional point, which is the fact that when you are describing a system in which you have some possible places for some possible trajectories for the system to take, this is the usual two-slit experiment. Everybody has heard about it. And you know that when you want to describe that, you have to add the potential ways in which that behaves. and the probability to obtain or to have one specific location for the final particle can be computed as the sum of the amplitudes for each one of the places, for the amplitude that corresponds to that final state, final place. And we have to sum them all up and then square the result. And that gives you the probability for that final place, that to reach, for the particle to reach that place in the screen. Now, a simple question is what happens if I add another hole in there? So what do we need to do if we add one hole there? Can you type it? How should I change my calculation in that case? Anyone? So let me ask. Okay, Elson. Elson, can you hear me? Okay. Okay. So yes, Elson. So what happens in that case? How do we change the calculation if we have a third hole in there? I'm sure you're typing. An additional state. Well, not quite a state, but one possible trajectory actually. Okay. So the states would be basically this one and this one. And what we would be adding is this one here. Okay. But yes, so basically we need to add three potential, well, one additional potential path for the particle. Now, I imagine that some of you have heard this, this idea that, well, what happens then if you start putting more holes in between? Then you would need to add, if I make another hole here, then I need to add another one. And if I put another hole here and here and here and here, then you start to need to add a lot of potential paths. And actually, you can see then that if you completely remove the wall in between, what would happen? So let me ask somebody else. So Sean. Maybe you can tell us.
Go straight to the point.
Straight to the point only?
Yes.
Okay, that's one possibility. Any other idea? Thank you. Any other volunteer? Well, in principle, yes, straight to the point, but why straight to the point? Maybe we can elaborate on that. Okay, Xiaofeng, yes, path integral, exactly. So what's happening is that basically, if you remove completely the wall, if you think about it in terms of adding more and more holes, basically what you were doing, with every hole you had to include other paths, okay? And then when you go to the limit where there's no wall, basically you have to integrate all potential paths from the beginning to the end. And that's actually what is represented by the path integral. So basically what you have to do is add all possible paths, all not only all possible, but all imaginable paths from the beginning to the end. All of those will be added. Even things are as strange as this one that I just drew. Okay, so that's precisely the idea of the essence of the path integral from Feynman, that you need to add everything. And one crazy result from that is that when you do the path integral, when you add all possible trajectories, it turns out that all the crazy ones have such a high frequency or high variation in the quantum mechanical phase that basically they all turn out to cancel each other or to cancel themselves. And the only one that survives is a classical straight line. Okay, so far so good. Any questions? Okay, so that's first step. So basically we're saying that quantization kind of leads us towards the need to add all potential ways in which you can go from one place to another. Now the next step is what happens when we talk about high energies or short distances, when we are aiming at elementary particles. Basically what happens then is that first you need to account for the fact that from special relativity, we know that high energy means that you also have the possibility of creating mass. And then that means that we cannot avoid particle production. And even for low energy, it turns out that considering all paths, when you are talking about the quantization of a full field, that necessarily brings multi-particle states, because you can have this creation of new particles out of just energy, and then one particle can become a couple of them and then be reabsorbed as long as some rules are respected. So basically what happens is that in a region of space-time, every space point will have a corresponding value for the field. And here we have a couple of points, for example, at x1 and xn, and at time 0. And what we have is that at every point in this region of space-time, you have a field. What happens, similar to what happened here in classical mechanics or in the one particle system, where you went from one particle with its own position and momentum to operators. What happens here is that now every single point of the space-time region that you're considering will have its own field value, and what we quantize is the field itself and not the position of a specific particle, because the field can produce and destroy particles on every place. So basically what happens is that now what we quantize is not the position, but the field. And then what we consider is that this region of space-time has an infinite number of fields, each one of them quantized as a set of harmonic oscillators. Okay, so the excitations at each point, those are the ones that we constitute the quanta of that field. And then what we want to know is, for example, we want to know just the analog of this picture here, where we have an initial position and a final position. Here we also will think about an initial position and a final position for a particle, but what we want to add is something different now. So we have this specific configuration, or two configurations: an initial configuration of the field, where you have all space-time around it, let's say empty, and you have a particle here. So the field is excited over there. And your final configuration is also an infinite number of field points. but with only one particle over here, okay? So that's what you want to sum over now. But now what you need to consider is all possible histories, and those have to, you need to understand all the possible ways in which you can go from that configuration, that infinite number of simple or of quantum harmonic oscillators, to that configuration. And that basically means that you have to have all possible ways in which the initial particle, in which this particle may have traveled to here. So one possible way, and let me just use one of them, one of these. So one possible trajectory would be this one. Another possible trajectory would be this one, in which suddenly it creates two particles, which later, let's say that this creates another two, but these are reabsorbed, and then this is absorbed with this one, and that goes towards that one. Okay, so those are two possibilities, because now that we need to consider the possibility of creating particles, we need to add all these other potential histories. Now it is not just a matter of adding different trajectories, but also different topologies of the reactions. Okay, so what we will learn in this section is basically how we can do that sum of histories, and basically, or specifically, what are the potential history elements that we can use. And you notice that here, the really important thing is what kind of diagrams, what kind of combinations of particles can be used to construct the potential histories. And those are precisely what we call the Feynman diagrams. So far, so good? Any question? Okay, so let's start with the first set. So the simplest one is just electromagnetism and basically the theory of quantum electrodynamics. So it turns out that for electromagnetic phenomena, basically everything that we have seen in electromagnetism ultimately reduces to this type of vertex. So basically what we need to consider is the ways in which the electromagnetic field can reach from an initial configuration to a final configuration. So what we need to consider is these combinations of that vertex and only that type of vertex. So basically what we see, and we will represent it also always with, well, in our class, normally, most of the time, with time going from left to right. And basically what we see here is an electron entering, then emits or absorbs a photon, and then it exits our region. So basically what we are thinking is this is time zero, then at another time, then emits or absorbs a photon, and then after that, you only have the electron again. So far, so good? Okay, then. Now, one thing is that it's only this type of vertex, but give me a second, okay. But this particle here can be any charged particle. If a particle has charge, then it can participate in this kind of interaction. Now, combinations of this type of vertex, so basically this is our building block, but we can combine it in all possible ways. So basically, for example, here we have the same vertex. Notice that it is always a charged particle that keeps going after the interaction and a photon touching it. Okay, that's the topology that it needs to have. So here we have the same thing. It's a charged particle that just continues after interaction with a photon. Now, that photon can, of course, interact with some other particle. And this is one specific process. It's also an electromagnetic process that can be described through these diagrams. So basically here we have a total process in which you have two electrons coming in. So if you imagine at time equal to 0, we are here. So let's say that we have an eye looking at this. And when you start looking at it, you only see two electrons. And then at the end, at time t1, if you look at it, you have two electrons coming out. So the process that is described here is that two electrons were coming in, they exchanged a photon, and then at the end you have two electrons coming out. This would represent Coulomb repulsion or molar scattering. So it is Coulomb repulsion because these two are electrons, so they have the same charge. So what happens is that upon exchange of an electromagnetic interaction, they will, or if the theory is constructed correctly, it should tell you that they will separate. Now, the fact that these lines are coming closer and then going and then separating from each other here is somewhat of an accident. The important thing is just the topology of this. Okay, we can draw them in many different ways. Now, one thing that the quantum field theory has been developed to achieve is Lorentz invariance, or the fact that it has to treat very symmetrically space and time. So that means that if we have one diagram like this, we can also rotate it in space-time, and whatever we get should also be a potential diagram. If this is, sorry, if this diagram here is allowed in nature, then all its variations, all its twists and turns should also be allowed. So if I take this one and I rotate it like indicated here, then I end up with that diagram. So you can see that basically this one here is this one, etc. So you can see that it is the same diagram, just rotated. And what we see here is a diagram that should correspond to another process or to a physical process, and basically it is. So you can think about it again as two particles. Again, let's consider an observer looking at it here, then here, etc. So what you see is that the observer that is looking at this over here sees two particles coming closer together until they interact, until they get so close that they produce a photon, etc. But the point that is interesting on this particular one is that the observer that is looking at things at this time sees a regular electron, but then there's this other particle that is like an electron going backwards in time. And that's precisely how the positron is described. So basically, that guy here is an anti-electron, which we call a positron, as I mentioned before. So basically, that diagram corresponds to an electron and a positron coming together, annihilating into a photon, and then the photon turning back into an electron and a positron. So this is the electron coming out, and this line that is coming that way on time is something that is very much like an electron, but it has a strange time dependence. Okay? So now here, that specific diagram is called Baba scattering, and it corresponds to the attraction of opposite charges, because the electron and the positron have opposite charges precisely because of the way that the positron behaves. So that's the same diagram, but it turns out that for that specific case of, now think about again what happens. The thing that we can see is the initial and the final state. That's the only thing that we measure. What happens in between, and we will talk more about that later, but basically we have no access to what happened over here. But this is one representation of one possible history in between. But coming back to the idea, so that's one potential process that can happen between the electron and positron from the beginning to the end. But another thing that could happen if you start with an electron and a positron and end with an electron and a positron is this new diagram, in which instead of them annihilating into a photon and then the photon decaying into them too, we can have this other possibility, in which you have the two of them exchanging a photon, and it's still a valid diagram for the process of electron-positron going to electron-positron. When we compute anything about this process, we need to use these two, just as we need to add all the possible histories in the two-slit experiment, well, the two possible histories in the two-slit experiment. Here we need to add at least these two ways for this to happen. Any questions so far? Okay, that's an interesting question. Is there evidence that positron experiences opposite time flow? I will come back to that later, but basically, yes. And one of the most compelling evidence in physics is that it works, and this works extremely, extremely well. But we will come back to what is this thing of a strange opposite time flow later in the course. But yes, the answer is definitely yes. There's a lot of evidence that it works like that, and it actually should. I'll tell you why later, but we cannot escape from it. Okay, so now here are other diagrams that use all the same vertex, the same type of vertex twice. So notice all of the things that we are describing with that specific vertex, just building up more with that one. So we have, this is one. Notice that it is just two, we are assembling two of these vertices, and that corresponds to pair annihilation. So we have an electron and a positron annihilating into two photons. So at the beginning we have two particles, or an electron and positron, and we end up with two photons. So that's a physical process. Here's another one, which is the opposite of that one, which is pair production. We have two photons becoming an electron and a positron. Here's another one where we have an electron and a photon coming in, and we end up with an electron and a photon at the end, after having exchanged, well, somewhat interacted through a photon, an electron. So that is Compton scattering, actually. Now, notice that basically what we are doing here is taking all possible ways in which this, in which we can twist these lines here. If you imagine that these were made out of wire, basically we could be playing with this in space, and all of them are actually potential processes. So what we're doing here is, for example, I twisted this to go to the other side, while this went to the previous side, to the past. And basically that is allowed because we are, again, describing or using a description that treats time and space in the same footing. So a lot of this can be done. And basically that is closely related, or actually very, a way of describing in much more detail what we used to call crossing symmetry. This idea that we could move particles from one side to the other by changing to the n-type particle. It corresponds to some sort of invariance of these diagrams. Now, this opens an interesting possibility. If we, let's say that we have these three processes and we are an observer looking at this from below here, or at this time. Yeah, everything happening in this slice of time. So we have these three processes. We see that there are this positron and an electron that become two photons. And we have this photon coming in and that positron coming also in. And they exchange some momentum. And then you end up again with a positron and a photon. And here we have two photons producing a pair of an electron and a positron. So those are different things that can happen, but nothing, of course, excludes the possibility that those particles go on to do something else elsewhere. So basically, you see, for example, this, this electron and positron that you see there actually continue to be the same line. Well, they could be the same line as some other process that you were looking at later on. Okay, so it's a very interesting possibility that you have several of the particles that you see could be some continuation of lines that you had before. And actually, there's a very curious exchange that Richard Feynman mentioned in his Nobel lecture, saying the following, that, well, just reading Feynman, I received a telephone call one day at the graduate college at Princeton from Professor Wheeler, which was his advisor, in which he said, Feynman, I know why all electrons have the same charge and same mass. Why? Because they are all the same electron. Could that be the case? Can you say in the chat box, if you say yes, is it possible that all electrons have the same particle? Who says yes and who says no? Come on, everybody, just type yes or no. Just I want to see your opinions. Nice. No? Anybody says yes? Hard to imagine, yes, but plausible, maybe, no. No. Okay, so there are several no's. Why not? Anyone that said no, can you please unmute and tell us why not? Don't be shy, it's not a problem. It's not graded. Okay, so let me ask somebody. There's one message. Because of causality. Causality, but if causality was a big problem, then what happens with these ones? So here we have the same line coming in and out, and that's pretty much happening all the time. And causality seems to be a little bit shaky here. Any other, do we have any evidence that could tell us that maybe this is the case, or maybe it isn't? It is not? If all electrons were the same line, is there something that you could predict about the universe overall? What could you tell? What would happen? We see more electrons than positrons. Yes, if everything was the same electron, then no matter how complicated you make the full thing, when you take a cut anywhere, you should see the same number going one way than coming the other way. So we will need to see as many electrons as positrons. And well, maybe you could think, well, possibly all the all the positrons are far away in the universe and all the electrons are around here. But as far as we can tell, everywhere in the universe, everything is made of matter. If it was not the case, then a lot of there would be there's gas everywhere, and there would be some regions in the universe that would be producing a lot of gamma rays because there would be some interaction between a lot of matter and a lot of antimatter. But it's not a complete. The idea is not ruled out completely just on the basis of logic. Okay, but as far as we can tell, most of the universe is made of regular matter, and then that means that it seems to be that most of the lines that are visible are electrons. So that apparently rules it out. Okay, so questions so far? Okay, if not, then let's move on. So why would we do not need to stop here, because we can add some more vertices. So for example, we have this one. So now instead of just combining 2 of these type of vertices, now we're combining 4 vertices. Or here also with 4 vertices. For this one, all of these have 4 vertices. And all of these are examples of processes in which you start with 2 electrons and end with 2 electrons. So all of these would be other possible histories for molar scattering. Now you see that there are a lot of internal lines here. So there are several photons going around, even in some cases, electron-positron pairs. Yeah, so we here what we would see in slices of time would be that suddenly there's, well, let me just make that large and let me just see, make sure one thing. Okay, so in here, if you were an observer just looking around at different times, here you see 2 electrons coming in. Then at this time, suddenly out of the vacuum, an electron-positron pair comes out of the vacuum, and then the electron exchanges a photon with your other electron, and here the positron exchanges a photon with your second electron. So, and eventually, the electron-positron pair comes back and annihilate into nothing. And then later, you can see also, you go back to see only the 2 electrons that you originally had. Okay. Now, all of these internal lines that we have, this particle over here, those particles over there, they are actually irrelevant for the observed process. What we see, the thing that we compute our quantum mechanical results, our theoretical predictions, is basically just the things that we measure, which are the initial particles and the final particles. The rest we call virtual particles, and they can be thought of as some sort of mechanism for the process, but this is just something that helps us understand or describe things. But overall nature, what nature does is to include all of these potential terms into that. It's maybe that it is just a matter for us to think about it. So we should not think too much about these as really physically happening, but they are ways in which we can understand it and compute it. Now, the external lines are the observable particles, and they are the ones that specify what physical process we are talking about. Now, one thing that we have to be careful about is that there's only one primitive vertex. Just once we start drawing these things and putting them together, it sounds tempting to use some other combinations. For example, it's not hard to just draw these things. For example, this one first with 1 line here and then 2 lines, 2 photon lines, or 2 photon lines coming together at the same point as a charged particle line, or even something like this. But all of those are not are forbidden or are not included in what nature does. And the proof of that is that our description based only on the other vertex is extremely precise, is extremely accurate in making predictions. Okay, a few more points here is that Feynman diagrams, just be careful, they do not represent trajectories. They only represent interactions. And each diagram, so the only thing that's important on them is the topology, not whether two lines are closer at the beginning or at the end. That is really not important. The only thing is what touches what, and what lines are in the initial state and what lines end up in the final state. Now, another thing is that each diagram represents a number, and it's a very well-defined integral that we will describe later how to obtain. And that's one of the big contributions of Richard Feynman, which is how we can express every quantum mechanical process in quantum field theory as a sum of diagrams, and then how to go from the diagrams that are very intuitive to obtain or to construct, how to go from the diagrams to the prescriptions, to the mathematical expressions that they correspond to. That link is given by what we call the Feynman rules to obtain that those expressions. Now, for a given process, which is basically a set of external lines, the sum of all Feynman diagrams with those external lines describe the process. So that's what will give you the probabilities, the momenta, the angular distributions, etc. So basically, we need to consider all possible Feynman diagrams compatible with those internal incoming and outgoing lines. There are infinitely many, for any particular process, we will have an infinite set of diagrams that have those incoming particles and those outgoing particles. But the thing is that every vertex, once we learn how to compute the number that they correspond to, we will see that every vertex brings a factor of alpha, which is roughly 1/100. So basically, that means that the infinite sum that you need to make will turn out to be convergent. So it turns out that all processes in nature can be built from these vertices, or this kind of in this way, as far as we can tell. And I already mentioned that physical processes are defined by the external lines. So the observable particles are those external lines. They define the initial and the final states, and their masses are the correct ones. While there's a hint that for the internal lines, that is not the case. They do not, if you compute what is the expected mass of a photon inside those diagrams, it will not turn out to be 0. Now, the transition amplitudes that we will need for pretty much every quantum mechanical calculation or any calculation for experimental prediction will be a weighted sum of all possible histories between those external lines. So basically, once we have defined the incoming, once we say, I want to go from electron-positron to electron-positron, then the process will be determined by the sum of all possible histories inside. And basically, this means that you have to add all these, and in some cases, you will have to consider the fact that some symmetries require you to add to take into account some multiplicity factors. We will talk about those later. But basically, that's how we obtain the amplitude for a particular process. And now notice that once we know that these diagrams actually represent the series of an expansion, we can see how this specific value, the amplitude for that process, is equal to the sum of this term plus that term plus etc. the more vertices you have, the smaller the numerical value will be. And it is relatively easy to imagine and find the simplest ones, and those are the leading orders. And you will see this often in particle physics, such as the LO. And after you have the leading order, for example, here, this is the simplest diagram that we have for that process. There's a missing one, but we don't worry about it right now. Then we have a few of those that are next to leading order. So we call that NLO. And then you may want to also compute the next to leading order approximations. And well, these are terminology, these are ways in which we describe how many terms you have included in your expansion. Sorry. So for higher order corrections, often it is important to have analytical machinery, meaning computer-based code that can compute a large number of Feynman diagrams. So here's a simple example, or an example some years ago. They computed close to 13,000 Feynman diagrams for the computation of the electron G-2, electron magnetic moment. And that's a result from 2012. Of course, by now we have much more complex computations. Okay, now for all this to work, or the way that all of this works, is that energy and momentum should be conserved in each vertex. And as a consequence, it turns out that that implies that we'll force that they meaning energy and momentum, will be conserved in the full diagram as a whole. Now, one question, does the primitive vertex represent a possible process? So we are building everything out of this particular vertex. Is that a possible process? Can you see in nature one electron coming in and producing an electron and a photon? So can you type yes or no? What do you think? Again, it's not a problem not to be right. Just I want to see what you think. Yes, in the atom excitation could be. Somebody says other yes. So everybody, please type yes or no. I want to see how many yeses and how many no's we have. Yes, 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 yes. Everybody say yes. Okay, so what is the center of mass energy at the beginning? The total energy at the beginning is what in the center of mass? Anybody? Anybody remembers this one? Yes. So at the beginning, we have mc squared. That's the energy of a single particle in its center of mass. What is the final energy of this process? First, we have two particles. And if momentum is conserved, they should be going in opposite directions. So this has to have some momentum. So that means that the energy of that particular electron is equal to mc squared. Well, p squared is m squared c fourth plus p squared c squared. Do you remember that? So already this energy is larger than this energy here. And not only that, we also have a photon coming out. So it turns out that the basic vertex that we are using is not a valid process by itself. It's the process, is the building block, but it cannot happen by itself. It cannot happen. We cannot have that process only like that. It does not conserve energy. Now, maybe it is just a matter of how we rotate it. What about this one? So is this a valid process? Here is the same vertex, just rotated in such a way that we have, remember, the time is going that way. So now we have 2 electrons coming in and 1 photon only coming out. Is that possible? Can that happen? So can you say yes or no? Yes, yes, yes. Okay, no. Okay, we see any other no's? Okay, it seems like it could, but so think about it. What happens here? We can always build a center of mass frame, right? So in the center of mass frame, what is the total momentum of the system? Zero. That's the definition of the center of mass frame, yes. And then can we, what is the center of mass momentum? What is the momentum in the center of mass frame for a photon? We cannot, exactly, we cannot go to that frame because it's already at the speed of light. Or said in a different way, there's no frame in which the photon can exist without traveling at the speed of light. So again, this is an invalid process. Okay. So again, it is not a valid process, which one thing that you can notice here is that if this was not valid in one specific orientation or in one specific instance of its orientation in space-time, then since all of quantum field theory is made so that things are Lorentz invariant and that there are some that it works in all frames, then if it is not valid in one frame, it's likely invalid in others. Now this is not extremely general, but well, you see that that in this case it works. So the basic process cannot happen by itself. We cannot have 2 real electrons producing one single final real photon. It can happen inside a more complex diagram, but not by itself. Okay. There's a question. Thank you. What's the question?
I'm just thinking because previously in a few slides back, you have a case where you have the pair annihilation, where you have 2 photons coming out. And that process is allowed, but this one is not allowed. And I'm wondering, why does the previous one allow? Because
very good.
Yeah.
Very good question. Thank you. So let me just put it here. So you have pre-annihilation, which was like this. So what happens here? In the case of this one, we cannot have a single photon because a single photon has no center of mass frame, or there's no frame in which you can have it exist and be at the speed of light anyway, okay? But here, you have 2 incoming particles. The center of mass momentum is 0. And as long as the 2 photons come out in opposite directions, you can have 0 momentum, a center of mass frame, because the total momentum will be the sum of the 2 vectors, the momentum of this one and the momentum of that one. And you can have a frame in which you have both a total 0 momentum and the 2 photons going each at the speed of light. Okay?
Right.
Okay.
This is a follow-up question. Can I merge the 2 vertices together to make a 1 vertex?
To make 1 vertex.
In annihilation, you have 2 vertices. Can I merge them together into 1 vertex?
Like
Yes.
this?
Yes, yes.
That will be not really. So basically what happens is that if you look at it from lower energy, maybe you can think about it as that. You can think of that as a representation of something that's happening there at low energy. So at low energy, you can think of it that way. but the description actually has to correspond to this. So we will talk about that a bit more later, but basically in many cases, when you go to higher energies, you start to notice the effect of whether or not you have an intermediary particle here. Okay. At low energies, it will look like it's a single vertex, but that will be included in the description, and it basically corresponds to let some variables of your description be very small. So yes, you can describe it that way, and actually, when we get to the expressions that that corresponds to, you will see that at very low energies, some of those will just disappear. Here, it would be like the mass of that electron suddenly is not there anymore. Okay. So in short, the answer is yes, you can describe it as a term that represents the full interaction, but the more precise description will actually be the one that takes into account the fact that there's an electron going in between. Okay. Okay, thank you. Very good questions, thanks. Okay, so okay, I think, well, let me just go one more. Let me just double check. Where is a good time to make a pause? My computer especially slow now. Okay, just a second, sorry. Many things open. Okay. So well, let's add a few more, and then we'll have the first break, the break. Okay, so then, so as I mentioned before, any charged particle will interact with the photon. So not only the lines that we have here need not be only for electrons, but any charged particle would be able to participate here. So here we have a U quark interacting in the same way as the process we were just talking about. And does this sound familiar? Can you notice what process this would correspond to? Is there a physical, what physical process could this describe? Annihilation, yes, it's a type of annihilation, correct. But what if these two U quarks are actually bounded together? What would that be? It's a U bar bound state. What is that? A meson. Which meson? The pion, yes. So that is pion decay. So basically that specific diagram corresponds to the decay of the pi zero. And another interesting point is that pi plus and pi minus, which are other particles, not UU bar, but UD bar, also, well, they also exist and they also end up decaying. But the fact that this guy actually has already two particles that are very, let's say that they like to do this kind of thing, they are likely to undergo this kind of reaction, turns out to make the pi zero much easier to decay. It has a much lower lifetime than these guys. Okay, so well, that turns out to also describe this. Okay, now let me ask you to try a quick exercise. And try not to, don't look for it on the internet. Just try to see whether you can use the diagram, the basic diagram, to build the Delbruck scattering. So this process in which you have 2 incoming photons and you end up with 2 photons. How would that look like? So try to draw it. So you have 1 photon, another photon coming in, you have a photon and another photon coming out. How can we combine the basic diagram from that we have been using all over, many pieces of this to fill up this void? How can you make that happen? Give it a try in a piece of paper or just your iPads or you're working. Let me know if anyone gets how to do it. Anyone? I'll give you a minute to try. Okay, I will not say anything yet. Just this try. Okay, did anybody do it? I already saw one suggestion. Anybody else? Okay. So can you just let me know if you were able to make it? Just say yes or no. I want to see many yeses and nos. It's okay to say no. That no problem if you couldn't. Okay. Okay. Very good. So well, as you probably noticed, basically the way to do that is this one. Okay. So that's a possible process. That's the way in which photons can interact with each other. But there's something really fun about this, or really strange about that process. We have Calvin's homework all over again. The way in which photons scatter from each other is through the existence in between of a particle that is just circling in time forever, being passed from one to the other and just making that happen. That's a really strange thing that is actually extremely precise in describing the way that these particles interact. Okay, so basically, this thing that was happening with Calvin's homework turns out to be quite a good description of what happens with photons. And we will see that kind of loop many other times later. Any question? So do you want, we can give a 10-minute or 5-minute break and then finish, or do you prefer that we keep going? Either way is fine. Who wants a break? So I guess keep going. Okay, so I'm fine either way. Okay, so then let's keep going. So that's for quantum electrodynamics. So see all the things that we could do only with this simple vertex. Now we're going to take a quick look at quantum chromodynamics. So basically here is very similar, but now color plays the role of charge. So basically, just as we had the basic vertex for quantum electrodynamics, for electromagnetism, what we will have now is quarks touching lines where the outgoing or incoming boson is a gluon. So just remember again, the photon is a boson, the gluon is another boson. So that's the particle that transfers the interaction. Here's the particle that transfers the strong nuclear interaction. Now, what happened will be that it's in similar structure, but there are some important differences. The quarks come in 3 colors, and notice that you cannot have a blue anti-U quark. You either have a U quark, which can be blue, or red or green, but let's say blue, or an anti-U, which would be anti-blue. Okay, so quarks have colors, and anti-quarks have the corresponding anti-color. Now, quark color may change, but not the flavor, meaning that if you have a U quark or a D quark, they cannot become an S quark or another quark by the strong interaction. We will later see other cases, but the strong interaction does not change the type of quark that you have. The quarks will keep their identity under strong interaction. But the color can change. And the changing color will be carried away by the gluons. So here we have, for example, a red incoming quark, which becomes a blue outgoing quark. And that means that the gluon, this gluon that is outgoing, we have to be red and anti-blue. Okay? So they will always be like that, as a color and anti-color or combinations of those. Similarly, for the force between quarks, at lowest order, we would have something like this, just quarks exchanging gluons, and because of that, potentially exchanging colors. So here we have a gluon, which, depending on how you draw it, could be red anti-blue or blue anti-red, but that's the one that is carrying the difference of the 2 colors that are changing, or the 2 quarks that are changing color in the interaction. Now, gluons have then 2 colors. It's always color and anti-color. And that, in principle, we could think of 3 by 3, because there's 3 gluons, so, sorry, 3 colors, so it would be 3 possibilities for each one of the 2 colors. And that would give us 9 possibilities, but there are only 8 gluons. We will talk later in more detail about how that happens. But, well, no, I'll come back to that later. Okay, now gluons do carry color, and this is a big difference. So gluons carry color, we already mentioned it, and that has a very important and very strange consequence, which is the fact that in contrast to photons, well, let me just come back. When you have 2 photons, when you have 2 photons going around, they do not interact with each other. You can have 2 charged particles, and they will be exchanging photons, but the photons that are coming here, this photon here, does not do anything about this other photon over there. They do not push each other or interact with each other to first order. We already have seen that there may be some scattering there, but it is a smaller effect. On the other hand, gluons, and this is because photons themselves are neutral. They do not have a charge, but gluons do have color, so they do interact with each other. So that means that they can have these kind of vertices. They do have those as elementary vertices, as basic vertices. So they do carry the color, and the color combinations work out correctly. So there is no self-contradiction or any inconsistency there, and that makes for a very strange phenomenology as well. So that makes the quantum chromodynamics phenomenology, the strong force possibilities, much richer than the quantum electrodynamic possibilities. And also it makes possible the bound states of gluons, these potential glue balls. Now there's one big problem with the quantum chromodynamic description, which is the fact that in contrast with the electromagnetic case, in which the coupling constant, or this fine structure constant that basically represents the strength of each vertex, in the case of electromagnetism or QED, that coupling constant is about 1/100, well, specifically 1/137. But the corresponding value for the strong interaction, alpha strong, is greater than 1. Now that's a big problem, because that means that if we want to use our perturbative methods, in which we basically represent everything as a series, as an infinite sum, where everything has higher and higher powers of the vertex coupling constant, you're in trouble, because that series is going to be divergent. So that would be quite, well, that basically kills our tool. We have this great tool to compute every process and the quantum mechanical amplitudes, but it would completely be dead because of that. So that would make it impossible to sum diagrams. But it turns out that we are extremely fortunate, because there's an effect similar to the dielectric shielding of a charge that comes to the rescue. So when you have an electric charge, you know that if you have it in a dielectric material, the material around the charge gets polarized, and that basically brings some charges closer, the negative charges, if this is positive, negative charges from the surrounding area come close to it, and that basically shields or makes it look like the charge was smaller than it was. Because if you are over here, then you have a lot of negative charges closer to the positive charge, and then it looks to you as if the charge that is in between is smaller than it was. So that kind of effect also happens at the quantum level, and the QCD version of this effect rescues our tool's convergence. Because, well, basically we have the quantum mechanical version of that effect comes from electron-positron pairs in the vacuum. So basically we have these kind of diagrams in which you have the creation and annihilation of virtual pairs that happen all over the place. And in QCD, we have, in addition to the quark-quark gluon vertex, we also have the gluon-gluon diagrams and the gluon loop diagrams like these ones. So we have these similar diagrams, but with gluons. Now, those diagrams, in the case of quark polarization, at short distance, increase alpha strong, and the gluon loop diagrams reduce alpha strong. And they depend on the number of quarks or number of flavors, and the ones that are due to gluon loops depend on the number of colors. Overall, that brings a dependence of this effect, the net effect of that sum depends on this factor. It's something that we will not compute, but it's interesting to know that overall, whether at short distances your alpha s will become stronger or weaker depends on the sign of that combination, where F is the number of flavors and N is the number of colors. And for the standard model, we have 6 flavors and 3 colors, and the number is negative. And in total, the net result of this is that this turns out to decrease the QCD coupling constant at short distances. That means that within hadrons, within particles bound by the strong force, quarks interact very weakly, and this is called asymptotic freedom. And basically, it means that when you go to very high energies or very small systems, alpha strong becomes small enough that we can do our sums, that our perturbative calculations, our perturbative tools in terms of infinite sums with increasing powers of alpha strong become convergent again. So, and that also has been measured extremely carefully to see the dependence of alpha strong with respect to energy, and it matches the theory perfectly. So it really is, it's really lucky for us that we can do that. So one final difference is that, as we mentioned before, naturally occurring particles are colorless, and we only observe indirect effects of color. So originally, when Yukawa mentioned this interaction within the nuclei of protons or neutrons exchanging some particles so that they could stay together, well, that allowed us to look for and find the pion. But now we know that things are a bit more complicated than that. So basically, since naturally occurring particles are always colorless, then the only thing that we can actually see in our experiments is the pion. But what it is hiding is combinations of quarks in which you have a proton, a UUD, continues to be a proton, still a UUD, but the exchange with other protons is through exchanges that include these middle-sized particles that are made out of quarks. But then what we see is only indirect effects of the strong force. So we do not see the gluons themselves ever, but always these combinations that are colorless. And finally, let me just check one thing quickly. Okay. Okay, and one final thing is that due to the fact that that gluons interact with gluons, that gluons are colored, then we mentioned before, let me just make it over here. So when we have two charges and photons exchanged between them, the photons themselves do not care about other photons. So if you have, just, we have this photon over here, it will not care that there are other photons around. And if you have a photon going this way, well, it will not, they can come out in any possible direction and they will not care that there are other photons around. However, with gluons, a gluon coming this way and a gluon coming that way will see each other in a way. So they will be able to interact with each other. And that actually turns out to make the gluon interaction into a very tight string. They do not let each other go much farther apart. So basically what you have is that all the energy that in the case of photons could be spread out in every direction because they don't care about each other. In the case of gluons, they concentrate the strong nuclear force into a string between the two gluons, between the two quarks, that basically has constant energy density. And then the farther apart you pull them out, you're just increasing the amount of energy stored in the system. And that means that at some point, that energy stored in the quark, in the gluon string, will be enough to pop out of the vacuum additional quark antiquark pairs, real quark antiquark pairs, that will be able to recombine with the original ones, so that in the end, you end up without being able to see single quarks by themselves. Always, whenever you do this separation, you turn out it's energetically favored to produce quark antiquark pairs to recombine with the other ones so that you come back to have a colorless combination. So this is what is called color confinement. And even when a lot of people were really doubtful about this because it looked like an excuse to say why we were not able to see quarks by themselves, it turns out to be somewhat understood in terms of the way that the strong interaction and the colored interaction behaves. This is not completely understood yet, but things are in a much more solid footing than before. I mean, we will see later on in the course how this is at least plausible to see. Okay, so that's for the first two interactions. So we have seen quantum electrodynamics and quantum chromodynamics. Next time we will come to the weird one around, the very strange one around. We will see that the weak interactions turn out to be always in some way weird, but we will come to that in more detail. So we will leave that for next time. Any final questions before we close? Nope. Okay. Yes.
I have a question about the gluon string you mentioned at the end, because at the very beginning you mentioned about the Feynman diagram. The lines doesn't mean anything; it only refers to the interaction. So I'm thinking, like in the photon case, spatially you can draw them like very in all directions, like separated, very sparsely separated, but then in the gluon case, you said they have to be very tight together. And that's...
Yes, indeed. Good point. The thing is that in the case of photons, again, it doesn't matter that we draw them like very separate. The thing is that they do not interact with each other. So regardless of how we do these diagrams, physically they don't care about the other ones going around. But gluons do interact with each other so that they do care. So they do have this interaction with each other. So we could draw them like this, but the fact that you have these additional interactions has to be included in your description. And what that represents in terms of the physical space is that they stay in a relatively contained tube. Okay, but yes, you're right that the Feynman diagrams do not represent space, but when we think about what that means in terms of space, that in this case it corresponds to that string. But here the important thing is that photons do not interact with each other, so they do not have additional photons going from one to the other, while gluons do. Okay.
Okay.
Very good. Any other question?
Yes.
At the start of the quantum chromodynamics, you said that you cannot have a blue anti-U. I'm not quite understand that statement.
Yes. So it's just to make sure that, for example, we have U quark and a U bar quark. So in the case of an electron, let me see. Okay, so for example, in the case of an electron is negative and the positron is positive. So the charge is determined by whether you are using a particle or antiparticle. It is the same way with color. So just to make sure that we do not think that we can have a blue, that if you have a quark, it has to be either blue, red, or green, or linear combinations, but it cannot you cannot have a U quark that is anti-blue. Yeah, it doesn't work that way. If it is a quark, it has to have either of these or their linear combinations, but you cannot have a U quark that is anti-red. That doesn't happen. If you have an anti-red quark, it's because it is a anti-quark. Is that
Yes, that is very clear. So basically, you can think of have 6 color, and 3 of them is belongs to the quark, and other 3 is belong to the anti-quark.
right? Well, it's 3 colors, and they correspond to quarks. And if you have anti-quarks, then it's the anti-colors of these ones. So it's the same 3, but just either themselves or the anti-color.
Oh, okay, understood.
Okay, very good. Good question. Thank you. Any other one? Okay. Okay, if not, then thank you all, and well, be safe, and see you next time. See you on Wednesday. Bye-bye.